All right, we are finally going to be in a position to resolve our paradox. So remember the paradox we had was that if you had two rods with matching excess charge densities, when viewed by a stationary observer with respect to the rods, they're going to repel, but if you move fast enough, the magnetic field will make them attract. So which is it? Well, now we understand better what happens when things move. If these rods start moving, the theory of relativity says that their length is going to contract. But if these rods are in motion, what doesn't change is the charges. So they've got the same amount of excess charge, but it's packed into a tighter space. So now what does that mean? Well, if we go back to Maxwell's equations, our electric field density, or the divergence of our electric field lines, how quickly they spread apart, depends on the charge density. The charge density here increases when the length contracts. Because now, if we only have half the original length, the same amount of charge is packed into half the space, so our charge density gets doubled. That means our electric force also gets doubled. So, as they speed up, the electric force becomes greater. Now, what happens to the magnetic force? We know the magnetic force on these two charged rods is going to be the current times the length of the rods times the strength of the magnetic field. And again, this is a cross product. Well, as these rods get faster and faster and faster, you're going to expect a little more current, right? Because these charges are going. But if you think about the entire rod, you've got the same amount of charge, but in less space. So the length is decreasing. The current is the amount of charge divided by time. And a moving clock experiences less time. That clock slows down. So what happens is that as your length decreases, which would decrease the magnetic force, your time slows down, which has another impact on the magnetic force. So if we go back to Maxwell's equations and we take a look at that magnetic force, well, that's going to be based on our magnetic field, but our magnetic field, how much that curls around, right, and how much force then comes out of it, depends on that current density, which is going to have some competing effects here, but the current density doesn't increase as quickly as the charge density. The charge density just straight up increases because all that matters is the length. The current density, the length is competing with the time. So while the charge density increases and produces that force perpendicular to the motion of the observers, the magnetic force changes to match. We've got the same effects here. If we want to deal with it on a particle by particle basis, as these charges are in motion, that velocity also shifts because of relativity, just like the charge density does. So yes, a moving observer will agree that now there is a magnetic force where there wasn't before, but that moving observer will also agree the increase in the magnetic force is perfectly balanced by the corresponding increase in the electric force. This is how it gets reconciled. The length contraction, time dilation, and change in velocities is exactly enough to offset the effects. So here, the paradox is resolved. And the issue was not a problem with Maxwell's equations. The issue was with Newtonian mechanics.